So hello everyone. Thank you for the opportunity to present this work. So I will talk about minimizing how we can design an approach to minimize the energy consumption of quantum computers. So this work is based on this paper, which is in PRX Quantum. It has a different name than the title of that talk, and it has been done with people who you recognize the face of, I guess. So let's start, and so let's first recall why we would like to build quantum computers. So we would like to build quantum computer because there are problems for which we know that the best classical algorithm to solve the problem will have a complexity that will go much quicker than on quantum computer. And then from that, it's expected that a quantum computer will save time. And when we look at this graph, it's also expected that they will save energy at some point, because you have much less operation to do for large enough problem size, so they will save energy at some point. But what is not obvious is the moment they will start to save energy. Because if you take a useful problem, you want to solve a useful problem, maybe the energy consumption for the quantum computer will be absolutely huge. For instance, you could imagine that you need 10 nuclear reactors to run your computation for a few hours. And this is first a problem of feasibility of the technology. So that's a first reason why we need to tackle this question. The other reason why it's interesting to tackle this question is because we could imagine application of quantum computer in which we do not aim to save time, but to save energy. And for instance, we could probably imagine example where we save energy before saving time. That's another motivation. So in this work, we propose a framework to optimize the energy efficiency and more generally the resource efficiency of quantum computers. And the goal is basically to put this transition the earliest possible, to make the computer energy efficient for the most smaller problem possible. So then we will apply this framework in a toy model, and I insist on that. It's a toy model of a complete quantum computer based on superconducting qubits. And there I will come back on the assumption after, and we will estimate the energy requirement to crack RSA, because it's a well-documented algorithm. So what matters in the talk is really the framework. So the framework is built on a methodology that is pretty simple in its principle. We introduced it, and it's called MNR for metric noise resource. So basically, the elements you have in this approach are first the metric. So the metric is one number that quantifies how good your computation is, how often your algorithm will succeed in implementing the task if you want. Then you have the noise. You also need to model the noise, because you know that noise is what will limit the success of your algorithm. So you need to model the noise. And you have the resource. So in that case, it's energy or power, but you could imagine many other resources. And in the middle, you have control parameters. So these control parameters characterize the architecture of your quantum computer. So they characterize which the compilation of your algorithm at the logical and physical level, for instance. They characterize the qubit. You can put the qubit temperature, the error correction scheme you use, etc. And basically, by tuning this control parameter, you will modify the amount of resource you need in your computation. And also, it will modify the way the noise acts. And then the success of your computation. So let me take directly a simple example. So imagine you work with superconducting qubits, and you know that by tuning their temperature, the colder they are, for instance, the more energy it will cost you to run the computation. Because then, think about Carnot efficiency. It's hard to remove heat at low temperature. But at the same time, it's good, because then you mitigate the thermal noise. And then, because you mitigate the thermal noise, you can reach a higher success for your computation. And then simply by understanding this connection here, you can ask a simple question, which is a minimization, the constraint. What is the minimum energy I need under the constraint that my computation succeeds, with the probability being something you find reasonable? And what we did is to apply this simple thing in a complete model of quantum computer, and we optimize its architecture. So I will not have time to go into detail. I just tell you roughly what there is in the model. So there is all the electronics that is driving the signal, that is amplifying the signal from the readout. So this is modeled. There is the heat conduction in the cable, the attenuation. I will come back to that point after. And basically what we do is we optimize the temperature the temperature of the cryogenic stage, the level of attenuation we put on the line, and the number of physical qubits per logical qubit. And of course, this parameter will modify the consumption, but also how the noise acts. So we need to understand again those two things. And we are doing quantum error correction based on concatenated code. I will explain why we took that code in one moment, but first I would like to give a very simple explanation of how error correction works. So when you do error correction, So here, what I explain is the formula will change for another code, but my explanation will work for any kind of code. So here we have a parameter k called the concatenation level. Basically, when you increase this k, you increase the number of physical qubits per logical qubit. Why do you want to do this? Because if the error of your physical gate, if you did not do error correction, was below a threshold, by increasing this k, you can make your error of the logical gate as close to 0 as possible, so you improve the accuracy of your computation. So there is a trade-off. You put more qubits, but your computation is more accurate. And so here, that's the last parameter we optimize, this k, which will tell us the number of physical qubits per logical qubit. So just a comment, why did we use thin code? So for people that are a bit familiar with error correction, the most popular approach to scale up is the surface code. There are different reasons for that. It has a high threshold, meaning that the hardware can be worse, but error correction will work. In some sense, you do not need a qubit as good as we would need for STIN, and the overall overhead for reasonable error rates will be less than with STIN code. But when we started this analysis, we really wanted to have a complete model for the quantum computer. We tried to not neglect any important source of consumption. In particular, in surface code, there is a costly, when you do error correction, you need a classical computer around to, from the measurement, know, oh, this qubit had this error, so then I need to feed back like this on my qubit to fix the error. In surface code, it's an open question. At least when we started this analysis, how much energy it will cost. While here, with STIN code, we can estimate everything analytically. It's a very nice code for that, and that's also another interest, which is we can run the minimization on a laptop that I will show after, precisely because a part of the model is analytic, thanks to STIN code. And so, yeah, sorry, and so this gives us the number of physical qubits, but also from the algorithm that is implemented at a logical level, we can compile it at the physical level. So we know at each unique time how many CNOT I have in my computer, how many Hadamard I have, and this will scale the consumption of the dissipation of the signal in the attenuator. Okay, so at this point, you sit down and you can write an expression of the power consumption of the computer as a function of all these parameters we can optimize. So now I move on to the noise. So this was one part, the power consumption. So now we need to understand how this parameter will affect the success. So here we took the simplest model you could have for superconducting qubits. So basically, this is an open system equation. And here the green part is if you had a unitary evolution, so that's the evolution you want to do on your gate. And in red here, this is the noise. So basically, you cannot do a perfect evolution. You will be perturbed by the noise, represented by this operator. And you have different terms. So N noise here first is the number of noisy photons due, for instance, to thermal excitation that will interact with your qubit. So if your qubit was exactly at 0 Kelvin in an ideal world, basically this N noise will be equal to 0. So you will not have any noise because of that. But your qubit cannot be exactly at 0 Kelvin, so first this thing will not be exactly equal to 0, but even if it was, then you will be limited by spontaneous emission, so your qubit gets entangled with the waveguide that drives it, because it interacts with continuum of electromagnetic mode, and this is what will, the inverse of this gamma is what I will call the qubit quality. It will define the lifetime of the qubit, so the amount of time it can store information reliably. And so how do we connect this noise model to the parameters we optimize? Through N noise. And actually I lied you a little bit because the qubit is not only sensitive to its temperature, but also to the temperature at which signals are generated. Because if you generate signal at room temperature, they will have a lot of thermal noise that will reach your qubit, and so your evolution will be very bad. And so this is why people put attenuator, which are big resistor, which they basically dissipate most of the signal that comes in, but they dissipate the useful signal, but also the noise. And then with that, you can mitigate the thermal noise coming from the signal generation stage. And these attenuators are the thing here, and so this purple thing, and they will dissipate heat, and it's taken into account in our consumption. And actually, the formula is a bit more complicated because you have different stages, but that's essentially the same idea. Okay, and now the metric. How do we quantify how good our computation is? So here we use the tool from error correction. We can define a probability that a logical gate fails. This probability of error depends also on the probability of error of the physical gate, because error correction, it depends on the quality of your physical hardware, which depend on all these parameters, the temperature, attenuation, and the number of physical qubits per logical qubit. And we ask, okay, we want the algorithm to succeed with the probability being 2/3, which is a typical value if you want to implement Shor's algorithm. because you can easily check the answer. And then it will give us this constraint on the parameter to optimize. And now we can do the minimization. So again, I insist on the fact this is a toy model. This is a kind of, you can think of it as a kind of alpha version of an energetic model of quantum computer. So there are optimistic and idealistic assumptions. So the main one is related to the fact of the code we use. So we use thin code, and basically, because we use thin code, we need to use very good qubits. So their lifetime here is 2 to 3 orders of magnitude better than the state of the art in superconducting qubits, to give you an idea. And also the estimation are strongly relying on the fact we use thin code. Then there is the classical part, so for the electronics used in a computer to generate signal, to do the amplification and so on, we consider 1 order of magnitude better than the state of the art, which is actually reasonable when you discuss with classical electronics engineers. And finally, the last important assumption is that the efficiency of the cryogenics is Carnot. It might look super optimistic, but actually it's not, because for large scale, Carnot is reachable. The Large Hadron Collider in Geneva, for instance, works at 20% of Carnot efficiency. So this is something that is possible for engineers. Okay, so now I will represent the power consumption as a function of the number of logical qubits and the number of time steps in the algorithm. And we have this kind of plot that we can have. So, for instance, under all the assumptions I said, the minimum power to run RSA 2000 will be 7 megawatts, and it will be implemented for a few hours. So you cannot deduce the time from this graph, I tell you, it's for a few hours. And this is the kind of thing that we can extract. And it's very important to understand that each point that you see here is the result of an optimization. So we optimize for each algorithm the full computing architecture. This is very important to understand. And so you see there are kind of brutal transition here. So technically speaking, the curve is actually smooth. It's just that it quickly varies on some of these points. And they correspond to the moment we need to add physical qubit per logical qubit. We are doing more correction, so we quickly increase the consumption. The fact that you see this quick transition is very model dependent. For a more energy efficient architecture, I will expect a curve to be completely smooth. You will not see by the eye the moment you add physical qubit per logical qubit. And we have examples like this in our simulation. So don't think that, because we also play with the temperature. So I will explain this better now. So this thing is the key point in understanding. This is the physics of the computer. And it tells you how a quantum computer uses energy if you want to make it energy efficient. So what you see here is the qubit temperature our optimization gives us. And let's start with that point. So just after a transition, meaning we added physical qubit per logical qubit. So because we added physical qubit per logical qubit, and we want to minimize the consumption while having a successful answer, what the simulation tells us is that you're doing a lot of error correction. So don't keep your qubit cold. Put them at high temperature. The qubit will be noisier, but it's fine, because you're doing more error correction. So this is a strategy to save energy here. And then you increase the duration of your algorithm, and then you have to fight harder and harder and harder the noise. And to do this, the qubit temperature decreases accordingly with the duration of the algorithm. Until you reach this point here, you have another transition, so now the qubits are very cold, and the script tells you, okay, you want to implement an algorithm that is longer, we have to fight the noise, and to be able to do it, you're forced now to add physical qubit per logical qubit. And when you do this, then you're doing a lot of error correction, so the qubit temperature rises again. So this is this effect here. The quantitative values are very specific to the code we use, but the intuition of how things vary is something that is expected to be quite general. Because you see that the qubit temperature depends on the algorithm I do at the logical level. So that's a connection between the software part of the computer and the physics of the superconducting qubits. Also the plot depends, of course, on the error correction code I use, because this is what gives this transition here. With another code, the thing will change, but still the temperature will vary accordingly to the code we are considering. And of course, the element of cryogenics engineering, because we want to, the reason why this temperature here is much higher than typical in superconducting qubits. So yeah, the noise model we use plays a role here, and also the fact that we use Carnot efficiency and so on. So this is a completely holistic effect. So maybe a few comments about what it means for a quantum computer to be energy efficient. So this is just to fix intuition to understand how energy is used. So here you have the energy consumption as a function of the duration of the algorithm. So what I say here, strictly speaking, is not specific to quantum computer. You could also imagine it in classical computer, but in quantum computing it will be very strong. So the energy used by a quantum computer will grow quicker than linearly with the time of the algorithm. So why is that so? It's obvious first that it increases at least linearly with the time of the algorithm because you're doing more operations, so you need to provide more energy to do your computation. But it should increase quicker than that because when your algorithm is longer, you need to mitigate the noise. And so you need to bring our additional energy to fight the noise. And an energy efficient quantum computer, so it should first have a curve that increases quicker than linearly with the time of your algorithm. And you should expect a curve that is quite smooth with no big jump, if you want, so, which actually indicates that the previous plot I showed you are suboptimal. There are many more optimizations we could do. And it also depends on the regime. As I said, the regime where the curve we see almost do not have jumps. So it is very system dependent. So there is a natural question. What about the scalability? How does the energy scale with the number of operations? So what we can say at least is that it cannot be worse than what is predicted by the quantum threshold theorem in terms of, basically the quantum threshold theorem gives you the number of qubits you need to scale up, but the goal is to minimize the number of qubits. Here we minimize the energy, so it cannot be worse than what is predicted by the threshold theorem, meaning that this extra thing here is actually a polylog, which means basically a logarithm up to some power. So that's how the energy will scale with the number of operations for an energy efficient quantum computer, at worst. Now there is a natural question, how much energy or power can we hope to save? So again, this is highly system dependent, this depends on what you want to do, the architecture. But at least in our example, we saw that, so basically if you do not consider Carnot, we took another efficiency which is motivated by literature, and we could show that our optimization can make huge reduction. So from the power consumption of 10 nuclear reactors to a few megawatts. I am not saying this will always be the case, okay? I'm really saying just we explored parameters that can be motivated by papers, and we found that at least in one example, which shows that in some example it can make the difference between you can or you cannot scale. So how to understand, for instance here, the optimization that are done are really not obvious. You cannot guess them by hand. And one reason I would like to give an example, for instance, sometimes it's smarter to put more physical qubit per logical qubit than if your goal was to minimize the number of qubits. Doing this can be more energy efficient because you can then make your qubit work at a higher temperature. So your computer is bigger, but actually it is smarter if you want to save energy because your qubits are at higher temperature. Okay, so I will just quickly go on that. With this framework, we can also explore regime where we can save energy before saving time. So they are based on specific case. I'm not saying it's a proof that we can have it, again, because this is a toy model and so on, but this is the kind of thing that we can explore with the framework. And one last thing I would like to talk about, which I think for me is actually probably the most interesting thing here, is that this general framework, so which is of course applicable beyond energy power, it's about minimizing the resource in general, is that it can provide a framework for a multidisciplinary team to scale up. So let me give you just an example of how to use it. So here you have the power consumption to crack RSA as a function of the qubit quality for a given regime in our script. And you have a green and a red curve. So the green curve represents energy efficient electronics. So that's, let's say, you have two scenarios, energy efficient or energy inefficient. And let's say that you don't want to spend more than 10 megawatts of power. So then if you're with this green curve, the engineer tells you we can do the green curve, then they say, okay, experimentalists, you need to reach this qubit quality. If you can reach this qubit quality, we can spend less than 10 megawatts while being sure to successfully implement the algorithm. And then the experimentalists tell to the cryogenics, oh, with this qubit quality, because we optimize the qubit temperature, you should put your quantum processor at this temperature. And you could imagine also a parameter which characterizes the smartest way to compile the algorithm at the logical level. So it can really be, you see the computer as a unique physical system, basically here. But let's say your engineer come another day and tell you, oh no, this is too optimistic, we cannot do that, we can only do the red curve. You say, okay, no problem. Well, no problem. There might be a problem, but I mean, it's possible. It's just the experimentalist needs better qubit quality, and then it shifted all the optimal parameters, the qubit temperature, the way the algorithm is compiled, and so on. So this is a clear way, for instance, for a community to work together with best choice to scale up. Okay, so I will conclude. So this is really the main point of that work. The quantitative value are just an example. The philosophy is really to see the computer as a unique physical system, and then you can do this optimization. Quickly, there is a new IEEE working group, so we are looking for experts. So Alexia already said it Monday. I just wanted to mention it again, and yeah. So that's it. So yeah, thank you for your attention.
Thank you, Marco. Maybe I'll allow one question before we go for lunch.
Hi, thanks for the talk. In classical computing, there's this thing called Rent's rule, which determines the number of interconnects in a classical processor and how it scales with the number of components. So it's a power law scaling with the number of components. And normally it would just be linear, but actually through optimization, they can get the exponent to be less than 1. And that has to do a lot with power dissipation in classical processors. So I'm just wondering, have you thought about devising a quantum Rent's rule or investigating that, since you could imagine that the points of contact that you need to perform control in your processor, particularly with all the physical qubits in the code, could involve some energy dissipation or channels that would, end up increasing your energy budget?
So, for instance, just to be sure I understand the question, so if we consider multiplexing, for instance, to reduce the number of cable, does it goes in the direction of what you want to hear, for instance? Because you can reduce then the interconnection, for instance, between the classical and the quantum processor. So just to be sure I understand,
or also, for example, there are approaches to quantum computing that uses global control, where you don't have to actually target individual qubits. You can have a control that targets the whole array.
Yeah, so indeed, this kind of thing can be used to find the optimal way to do this. So I can give you an example. For instance, in principle, you can use a single line to drive many qubits, because then you inject different frequencies to drive your qubit, and then you remove things. But the thing is that if you do this, you increase crosstalk. So it increases the noise. And so if you have a good model that tells you how much more noisy it is to do this modification of the number of interconnects, then you can put it as an extra parameter and do an optimization on that. And then you can see if basically the way you can reduce the amount of interconnect. That's a possible way to treat it.
Yeah, okay. I'm inviting Bill, maybe one quick question. Yes.
So I'm interested by the noise model that you use, actually, because you say somehow we need a good noise model, and then on the next slide you say we take the simplest possible noise model, which is a Lindblad equation and so on. Mm-hmm. When you derive this, you make a whole bunch of assumptions which are typically not really satisfied in an experiment. So my question is, like, given that you do optimization, simplicity must be an asset in a way as well. So how do you define what is actually a good noise model?
So definitely this is a toy model of a full stack. So we took the simplest thing everywhere to be able to because it's a proof of concept, this, rather than a detailed estimation. So now the thing is that what matters for a noise model is to accurately describe your device. So that's the most important thing. And then the thing is, so why I'm saying this? I'm saying this because if you start playing with parameters, for instance here with the temperature, you need to be sure that the description of your noise model as a function of the temperature keeps being accurate. So I think that the way to optimize things, to have interesting things from the optimization while being sure not making mistake on the noise model is to identify the parameter for which we have a good understanding of the noise. So for instance, the speed of the gate can be a parameter because on the one, if you do gate too quickly, you have leakage. If you wait too long, you have decoherence. And I think time and temperature are parameters for which we might have a good understanding. For other parameters, you should just put them at value you think are good if you don't understand really how they will impact the noise. So there's a brainstorm to do on the best parameter to optimize. Yeah.
Okay, thank you, Marco, and let's thank also all the speakers for this session.